All right, so we have talked about two chords that intersect on the circle's edge. That's called an inscribed angle. What we're going to look at here is some chords that intersect within the circle, or the intersection point occurs inside the circle's edge. So when that happens, the angles that are formed by those two intersecting chords are going to equal 1/2 the sum of the measures of the intercepted arcs. So in this particular case, what that would say, according to that theorem, is that if I add arc AD and arc CB and average them, in other words, half of the sum of those arcs, that's what's going to give me these two in the middle. The way you can think about that is this is not a central angle, this is not an inscribed angle, but they are equal to each other, and so therefore they have to incorporate both of these arcs here. Because the angles are equal to each other, so they have to use both arcs' impacts to figure out what they're equal to. So first off, what angle is congruent to AED? Well, AED is here. The congruent one would be the one on the opposite side, so angle CEB, and that's because they are vertical angles. Okay, so what two arcs do AED and your answer and angle CEB intercept? If we look at the intercepted arcs there, get my highlighter here. Arc AD is the intercepted arc. That didn't work out too well. Let's try that again. Arc AD is the intercepted arc for angle AED, and arc CB would be the intercepted arc for angle CEB. All right, so we have those. Let me just write them down here too. So angle AED is arc AD, and angle CEB is arc CB. Okay. So if the measure of the smaller of the two arcs in B is 58, let's put that here, and the larger of the two arcs is 76, then find the measure of angle AED. Well, AED is the same as CEB, and those angles are going to be half of the sum of these two arcs that those angles subtend. So if I take 58 plus 76 and do half of that, I'm going to get my total. Okay, so that's going to come out to 67 degrees. All right, and finally part D here, if AC is 61, so that's up here, 61, use the theorem above to determine the measure of arc BD and check your work to show it. So the measure of angle AEC is going to have to be half of the sum of arc AC and arc BD, right? But we also know that based off of linear pairs, if these angles are both 67 on the inside here, then this would have to be 113 degrees based off of the linear pair concept. So if that 113 is to be half the sum of these two arcs, I can just set that equal. 113 is equal to 1/2 the sum of 61 plus arc BD. Right? And that's just algebra from there. So if I multiply by 2, you get 226 equals 61 plus BD, and then just subtract 61, and my total for BD is 165. Okay? So the reasoning behind why this theorem works comes back to the work with inscribed angles. And so to prove it, we'll just go through a couple of things here. We want to prove that angle GHE, which is this angle right here with this purple dot, is equal to half the sum of arc GE and DF. That's the goal. Okay? So what can we state about angle GHE as it relates to D and G? Well, it's going to be equal to the sum because this is an exterior angle. So if I take triangle GHD and extend it, that extended angle is equal to the sum of the two remotes. So we have that from the exterior angle theorem. What do we know about inscribed angles? Well, angle D is going to be half of its arc. It's going to be half of its snow cone arc out here at GE. So 1/2 GE. No, not segment, arc. And angle G, if I take that out to its endpoints, that's going to be 1/2 of arc DF. Okay, so using the equality in A along with the results from B, prove the desired relationship. Okay, well, we said that angle GHE is equal to D plus G, so angle GHE, if I just substitute that, is going to be equal to 1/2 GE and that's the angle D part, that's the substitution for angle D, plus 1/2 df, that's the substitution for angle G, and so 1/2 of each of those angles would be 1/2 of the sum, which would be measure of GE plus measure of DF. And we have now successfully proven that if we have two intersecting chords, the angles between them are going to be equal to half the sum of the two arcs that they subtend. All right, exercise 3. We have circle K. Notice that none of these chords go through K, so we have no diameters here. So we just have two intersecting chords. They are perpendicular, so we have the right angle there. And arc BD has been marked as 126. We're trying to determine arc AC. All right, well, if we just use the concept of the angle being half of the sum of the arcs, we can say that 90 degrees is 1/2 the sum of 126 and x. So multiply by 2, 126 plus x, x must equal 54. And that's arc AC, so we've got it. All right, so going a little further down here, intersecting chords and segments. If two chords intersect with a circle, within a circle, the product of the partition segments of one chord equals the product of the partition segments of another chord. All right, well, let me just explain what that text is saying. If I let this be x and this be y and this be a and this be b, what I'm saying here is that x times y equals a times b. In other words, if I multiply the two segments of one chord, I get the same thing as if I multiply the two segments of another chord. That's what that's getting at. All right, let me take those out because we've got some numbers to insert here. All right, in exercise 4, it's telling us that AE is 6, that BE is 4, and that DE is 3. We want to know the length of CE. Well, according to what we just talked about, the product of one chord's segments, 3 times x, is going to be equal to the product of the other chord's segments, 6 times 4. So 3x equals 24, and x equals 8. All right, so that means that CE is equal to 8. And the fact that the partition segments have products that are equal is remarkable, direct consequence of similarity. So let's look at that a little bit. We've got the same diagram as exercise 4, but there's a couple extra segments drawn in. AC and DB are drawn in to connect the endpoints of those chords. We want an argument for why those are similar triangles. All right, well, angle ACE and angle DBE, if you follow their rays out, they both subtend this arc here at AD. Therefore, they're both half of arc AD, therefore they're equal to each other. So I've got two equal angles here. I have vertical angles here, and that's enough for angle-angle similarity right there. And as soon as I have angle-angle similarity, all the corresponding parts are going to be proportional. So looking at this, if I'm just taking the segments that were formed by the original chords, ignoring AC and DB for a minute, this AE segment corresponds to DE because they're both in the same position in the names of the triangles, and they're also both between the unmarked angle and the double marked angle, so those go together. CE and EB both are between the single and double marked angles, so they go together. And if I do a cross product, I get the theorem for the chords. I get the product of the two parts of chord AB equals the product of the two parts of chord CD. So there's your proof. But going forward, what we're going to do is take a piece times a piece equals a piece times a piece.